Okay, so this recitation is going to be about just part one of my bonus problem, because now that's the part that's required. So I've written it up here just in case there's any confusion. My bonus problem was originally a two-parter worth 1 bonus point, but Graham has decided that part one is now required, and it's due April 18th, and part two is the bonus part. So that means this whole thing is now worth 2 assignments total. One of them is required, one of them is bonus. Okay, so in case there's any confusion, that's the system. And I believe April 18th, I think that's a week from Thursday. So there will be office hours to help you out tomorrow, Sunday, and next Wednesday. So you'll have 3 rounds of office hours to get help, which hopefully is enough. But anyway, let's do the recitation. So first of all, this is originally you weren't going to know what the strategy that's required to solve it is because it was a bonus problem. But since Graham has made it required now, it's required under the category of the dynamic programming problem. This is the problem that we're giving for dynamic programming. So first thing I'm going to do is go over a bit of dynamic programming. You guys started that yesterday, is that right? Yeah. Okay, and what problem did you guys use as an example for? Oh, he did use Fibonacci? Log cutting? So he did Fibonacci and log cutting? He did both. Okay, cool. Well, great. So the example I had was Fibonacci, so I'll go fast if that's what you guys went over. In general, dynamic programming is when you're caching intermediate steps whenever you're solving a problem. So the idea is that if you compute something once, you don't want to ever have to compute it again. It's actually a pretty intuitive algorithm strategy. We save the results to subproblems in some kind of data structure. And that data structure is usually an array or a hash map. You could maybe use a tree, but usually it's just an array or a hash map. So, and the requirements for using dynamic programming are that you have to have optimal substructure. Did you guys go over optimal substructure? Yeah? Okay. Optimal substructure is when you can find an optimal solution by combining optimal solutions to subproblems. And then the second requirement is that you have to have overlapping subproblems. This is where you're using the solution to a subproblem more than once. So the idea with caching is that we don't recompute something if we need it again. Well, that doesn't do us any good if we're not reusing the data in the first place. If we have some algorithm where we're solving subproblems, but we only solve each subproblem exactly once, then dynamic programming isn't going to do anything for you. But if you do have overlapping subproblems, it's going to speed up your algorithm a lot. So yeah, and the classic example of Fibonacci is, the classic example of dynamic programming is Fibonacci. And this is it. Fibonacci is super easy to code. Just a couple of lines. You just have a base case and then a recursive case. And so I'm sure you guys have all seen this. And here's the recursion tree for that code that I just put up. Let's say if we're trying to find the fib of 7, then that's going to require computing the fib of 6 and the fib of 5. And computing the fib of 6, that's going to require computing the fib of 5 and 4, and so on until we get down to our base case, which is all these leaf nodes here. And as you can see, this is a pretty big tree. The size of this tree is the runtime of the algorithm. Every single node in this tree is some computation that we had to do. So this is a big tree, and you can probably tell just by the way it's branching that the runtime of that code that I just put up is exponential. You can see it here. It's exploding. So this Fibonacci implementation is exponential. And this is the tree for it. How long do you think it took me to make this tree? A long time? Yeah, it's a lot of nodes, right? It actually didn't take long at all. Because you'll notice there's some patterns here. This 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0. So what I did was I started with this. I just made that, right? And then what I did was I copied this and put it here and connected them with the 3. Okay? And then to get to the 4, what I did was I copied this, put it here, and then connected them with a 4. And then to get to the 5, I copied this, put it here, and then connected them with a 5. To get to the 6, I copied all of this, put it over here. You see the pattern? So it actually, as big as this tree is, it's really fast to make because you can start from the bottom here and copy and paste subtrees in order to build the tree as you go. And the reason that I can do that in this problem, or in this tree, is because Fibonacci exhibits optimal substructure and overlapping problems. These are the overlapping problems. Every single time I was able to copy and paste, that was an overlapping problem. So we can take advantage of that fact and write a much better Fibonacci solution like this. We keep track of some memory. That's the data structure I was talking about. In this case, it's a hash map. And then we first check the base case. Then we check the dynamic programming case. We check if whatever we're trying to compute has already been computed. And if it's not, we compute it like normal. So the benefit of this is that if n is already in the memory, if we've already computed the Fibonacci of n, we're not going to recurse at all. The function will execute in constant time if we've already calculated that value of Fibonacci. So that's dynamic programming. So this is top-down dynamic programming. Yeah, so that's a subtlety here. The way I did this was bottom-up. I was trying to, here I'm drawing the graph for Fibonacci of 7, so I started at the bottom and I copied and pasted up. This code is top-down. You would start by passing in the value of Fibonacci that you want to find, and then it recurses down and does the dynamic programming on the way down. So, yeah. Does it matter? So usually it doesn't matter asymptotically, usually. But there are cases where it does matter asymptotically, I think. It depends on your data structure. Like if you're using a tree, then it might end up being that the top-down approach is slower because you end up building the tree in some weird order or something. But even not asymptotically, often the bottom-up is faster. Because with the bottom-up, you're not, you can usually do it iteratively, so you're not recursing. Recursion takes time, and it also takes space. People usually forget that whenever you do any recursion, you're actually using a stack. And however deep that recursion goes, that's how big your stack is getting. So it's usually better, if you can, to do bottom-up iterative. But it's not always possible, and it's usually a lot harder. So there's that. Yeah. Any other questions about dynamic programming in general or Fibonacci? No? Okay. I don't, but I'm sure you can find it online. Yeah, I just whipped this up. Usually the top-down, like I said, it's usually asymptotically the same, and it's usually a lot easier to write. So, yeah. Okay, let's talk about NumWays. First of all, who has read through the problem? NumWays. Okay. And who has started on the problem? Okay. So, NumWays, the problem, is given the ranks of some players, and those players are ranked among themselves. Calculate the number of ways you could divide teams such that the size of the teams differs by no more than 1, and the sums of the ranks of the teams are maximally similar, and everybody has to be on a team. So the example is, let's say these are the ranks of the players, this means player 0 has rank 1, player 4 has rank 4, player 3 has rank 5. So we're pretending here that players are the index and their rank is the value, something like that. And so the solution, as I've written it out here, is just a list of the different teams we could make. So we could put 2 and 5 on team A and 1, 3, 4 on team B. That gives 7 on team A and 8 on team B. It turns out, you could probably see, that's as close as we can get. The requirement is that the sums of the ranks of the teams are maximally similar. Well, here there's an odd number, there's an odd amount of rank in total. This sums to 15, right? Yeah, 15. This sums to 15, which is an odd number. So it's impossible to get a completely even split as far as the sum goes. It's also impossible to get a completely even split in terms of the number because there's an odd number of players. So our goal here is to just have the team size differ by only 1 and have the sum differ by only 1, because that's the best we can do here. So we've got 7 and 8. That's maximally similar, and the size is different by no more than 1. So that's a valid solution. And then, of course, I just used these labels, team A and team B. It doesn't actually matter. We could have labeled it the opposite way. So here, 1, 3, 4 is A, and 2, 5 is B. So these are 2 teams. There's also those teams and those teams. So the answer here is 6. These are all the ways to split up the teams such that we meet all of these requirements. Any questions about the example or just the problem statement in general? Okay. So some things to note here. If there are n players, then the ranks of the players will be consecutive integers from 1 to n, because the players are ranked among themselves. So there has to be a first rank, there has to be a second place, because they're ranked among themselves, and because no 2 players have the same rank, because they're ranked among themselves. So we're in a world here where there's no 2 first places. Everybody has a unique rank, and there's n players. We have to start ranking at 1, so the ranks are going to go from 1 to n. That's a very important fact, and it's not explicitly stated in the problem statement, but it's a result of the fact that ranks are not just ordinary numbers. Ranks are integers. They start at 1, and in this scenario, you get this nice consecutive pattern, which makes the problem easier, harder? Makes the algorithm faster, which probably makes the problem harder. And then the other thing to note here is that the answer is always even, because we can always just swap the teams. So, I mean, on the other slide, you saw I had one solution, and then we just flipped it. We can always do that, and so we'll always have an even number of of ways. And that might lead to some optimizations. You might be able to do some clever stuff with that, and maybe cut the runtime by half or something. But it shouldn't be necessary. I didn't do that, so you shouldn't have to do that. But if you're coming in over time, you could try it. Might work. Okay. Other questions about the problem statement? Anything? Nope. Okay. So how do you solve this problem? Well, step 1 is I would start as soon as possible if you haven't, and I would keep going strong early. The problem will probably just take some iteration. You'll just have to go through a couple versions, I think, in order to get the solution. There's no way you can get straight to the answer. And along with that, use the private test cases. The public test cases are very generous with runtime. Don't think that the public test cases are any indication of the actual runtime you should be shooting for. The private tests are really pretty fast, on the order of several milliseconds. So just be aware of that. You don't want to get caught off guard, and submit at the last minute and then realize it's overtime. So start early and hit the private test cases often. Come to office hours. Some similar problems that you might want to check out. Knapsack and partition, similar, very similar. You might be able to get some ideas by checking those out. Knapsack and partition. They're not exactly the same, but they're similar. Step 2, consider the strategies. You've done divide and conquer. That's where you were able to break the problem into subproblems. That's applicable here. There are subproblems, and that's definitely going to be a useful way of thinking about the problem. There's search, like breadth first search, depth first search. That's applicable for graphs usually, and it's not obvious to me what the graph would be in this problem. I think there is a way that you could turn this problem into a graph problem, but it's not how I thought about it. So you're welcome to explore search solutions. I think there could be one, but I don't know. I don't think of this as a search problem. There's backtracking, which was when we had partial solutions and we could tell if the one was invalid. Do you guys think backtracking is applicable for this problem? Who thinks backtracking is applicable? Who thinks backtracking is not applicable? Yeah, it's not obvious at first, but backtracking is actually totally applicable to this problem. The requirement for backtracking is that we have partial solutions that are sometimes invalid. So here's a partial solution. Let's say the ranks go 1, 2, 3, 4. Okay, there's only 4 players, and the ranks go 1, 2, 3, 4. And let's say we put the player with rank 4 on team A, and then the player with rank 3 also on team A. That's a partial solution. We've put 2 of the players on a team. So that's a partial solution. Is it valid? No. We know it's not going to be valid because we know we've already assigned 2 of the players to one team. So the other 2 players are going to have to go on the other team if we want to have equal numbers. But if we did that, then the sum of team B would be 3, and the sum of team A would be 7, which is not maximally similar. You could do rank 4 goes on team A, rank 3 goes on team B, rank 2 goes on team B, rank 1 goes on team A. If you did it like that, I'm pretty sure the sums of the ranks would be exactly the same. So that's an example of a situation where you could have a partial solution that's invalid. Does that make sense? That's actually a very important part of the problem. You definitely don't want to be spending time on a potential solution, on a partial solution that's already invalid. That'll definitely put your solution over the runtime budget. If there's a way to prune some potential solutions, you're going to want to do it because there's so many different ways you could divide up these teams. You want to be able to prune as much as possible. So backtracking, something to keep in mind. There's flow. Flow also usually has to do with a graph, especially a flow graph. I'm thinking like max flow or min cut. Again, I don't see how flow would really be applicable because I don't know what the graph is. So again, there might be a solution that thinks of the problem like a graph and uses flow, but that's not how I thought about the problem. I think it would be more helpful to think of it as a divide and conquer, backtracking, and dynamic programming problem. And dynamic programming overlapping subproblems. Obviously, dynamic programming is applicable because this is the dynamic programming problem. The trick is figuring out what the overlapping subproblems are. If you can figure that out, you're going to be very close. Other questions about strategies? I know this is really vague. This is kind of a 3-step process to solving any problem, really, but it works.
So
Um, did you guys do the tiling dyno problem? No? Okay. Did he talk about it? Or tiling problems in general? No? Okay. So there's a problem called the tiling dyno problem, which is given an image of just black and white pixels, just on and off, zeros and ones, basically a bitmap. Determine if it's possible to fill in all of the black pixels with dominoes, with domino tiles. And domino tiles are 2 by 1. So is it possible to fill in all of the black pixels with dominoes without overlapping, you know? So, for example, if our image was that, let's say that's the black pixel there, it's not possible, right? Because if we put a domino here, we'd be covering a white pixel. That's not allowed. If we put it here, that's not allowed. But if this were our image, it would be possible. The domino would go right here. Right? So that's the problem. And the solution to that problem is actually flow, max flow. It turns out that you can convert the image into a bipartite graph and then solve max flow on it. And the result of solving that max flow will tell you in constant time whether it's possible to tile the image. So that's an example of a problem where it's not obviously a graph problem, but you can make it a graph problem, use flow to solve it. But like I said, I think this problem isn't one of those, but maybe. I don't know. Did that answer your question? Yeah. Okay. Okay, other questions here? Okay, step 3. Think about what kind of information you need. So, does the order matter in general? In the input, in your teams, does it matter? No. No, it doesn't matter. The teams are more like sets than lists. And the ranks, the list of ranks that you bring in, that's more of a set than it is a list. It doesn't actually matter what order those things are in. So it doesn't make sense to keep track of that information, right? Don't spend extra time recursing over a list when you actually don't care about the order of the elements. You know, so just don't keep track of order, basically. Do the teams matter in general? Maybe it was a leading question. No, they don't. All the question is asking is how many ways are there to divide up the teams? You don't actually have to pick the teams. So you don't actually have to keep track of who's on what team. All you have to do is keep track of the information you need to solve the problem. And the problem is how many ways, not what are the teams. Does that make sense? What makes a valid pair of teams valid? And what makes an invalid pair invalid? What information would you have to keep track of in order to identify a partial solution that's invalid? That's the information that is important. And maybe some other stuff too. But you know, think about the bare minimum of what you can get by with. The information you need is the information you want to recurse on, if you recurse at all. Somebody wrote an iterative solution, so it's possible to do it iteratively. But I think it's definitely easier to do recursively. So make sure you don't want to recurse on anything that you don't actually need, because then you're wasting space, you're wasting time, that kind of thing. So, questions about thinking about what information you need? I think this is the trick to getting this problem, is this slide. Really think about what you're actually trying to solve and what is and isn't relevant. A couple last things. Arrays are faster than hash maps. That being said, I did it with hash maps. It's totally possible to do it with hash maps. But if you're getting desperate and you need to get in under the runtime, you could try switching to an array-based solution. The players with the largest ranks are going to affect the sums more, right? And the consequence of this is that if you were picking teams and you were trying to make the sums as close as possible, if you started with the ranks that are low and then went up to the ranks that are high, you can kind of imagine how you might get stuck in a situation at the end where it's, you're left with just one player with a really big rank, and there's no way to put, you're likely to get invalid solutions if you go from small ranks to large ranks. So it's probably a good idea to start with the large ranks and work backwards, just because they're going to have a bigger impact. Who's played Blockus? Yeah, Blockus? Just one. You start with the large pieces first, right? Because they're going to invalidate the board. Yeah, same thing. Uh-huh. Yeah, I guess order does matter. Yeah, order matters in that sense, yeah. But keep in mind that the ranks are always consecutive integers from 1 to n. So here's a question for you guys. Is there ever a reason to sort the input? No, because you know exactly what's in it already. So you don't need to sort it. So the order does matter, but you kind of already know the order. The order of the teams don't matter, and the order of the input doesn't matter, but the order that you go through it does, if you see what I'm saying. Okay, other questions about the large rank players? Okay. Array lists are hashable. Super, super useful. And last hint is just watch out for overflow. There's a reason that the function returns a long. Turns out that the number of ways grows insanely fast. And so just be aware of that. It will overflow an int, like surprisingly fast. So I think that's everything. Any questions?